The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Welcome back to Element 14 Presents. I'm Clem, and this is one of my oldest 3D printers, and I just can't get rid of it. So in this episode, we're going to give it a new, better and improved life to still use this machine in 2020.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
This is my old workhorse 3D printer. I bought this in, I think, 2015. It's one of the very cheap ones that you could get back then. And yes, this one has also caught on fire at one point. But I repaired the board and I activated some protection measures in the firmware, and then it was a little bit more reliable. But still, it's just a cheap machine. But I can't get rid of it. I want to give it a new life. This is so old, it even says Mendel when you start it up, so it runs Marlin firmware 0 point something. So we are going to upgrade this to Marlin 2.0, give it some new features, upgrade it with modern dynamic stepper drivers, and also I make a dedicated PCB for it. So out goes the old Chinese board and in goes an Arduino Mega, a RAMS 1.4 to attach the stepper drivers to it, and my own PCB that gives it a second brain, like a secondary Arduino that controls some of the function that I want to add, and also have it monitor the power consumption and voltage of the critical parts like the hot end and the heated bed, and also have it measure the temperature at all times, so I know when I have temperature drifts or something goes wrong that would be not detected by the firmware. Of course, we start PCB design in KiCad with a schematic. Here's the schematic that I came up with. The main processor is an ATmega 328P. You already know that from the Arduino Uno, and of course we can use the Arduino IDE to program it. I have used an ICSP programming header on there to program it, so no USB connection, we omit that. And then we have a lot of I2C devices. I2C is a very handy protocol that allows you to connect multiple devices with just two lines, serial clock and serial data. The thing is, all these devices have a unique identification number. That is useful, so you can say, hey, device numbers so and so, listen to me, and then it does its thing. So what we need to do is attach all these devices in our design, and then in the code we have to respect which device has which identification. On some devices we can change these numbers, on some we can't, and I don't know which numbers these devices will have. So for two of them, we have three in total, an OLED screen and two current and voltage sensing units. And for these I'm using dip switches so I can influence that address. So in case they both have the same address, I can just flip a switch and give them unique addresses, so I won't have any confusion between them. If you have devices with the same ID on one bus, that will lead to errors. I snag the power directly from the Arduino, so I get my 3.3 volts for the OLEDs and my 5 volts for all the other stuff directly from the Arduino, so no additional power circuitry. And for the temperature measurement, I'm using the same circuit that is used on most RAMS boards or other 3D printer boards, which is a voltage divider between a thermistor, a known resistor, in that case it's 4.7K, and a little capacitor. And at the end of that, I don't use just normal header pins, I use these special probe clamps. These are connectors designed for thermistors, because if your connection is not perfect, your measurement will vary. And that is partially the reason why identical 3D printers can yield different results with the same components for temperature measurement. The PCB has arrived. Thanks to Isla.net for sponsoring those PCBs. If you want to get it, there is a link in the description, and there you find all the resources for the project, including a link where you can order that PCB. And to be specific, I had to do a botch on my issue of that one. So I had to reroute the power line. The version that is linked has already fixed that one. So no worries there, you don't have to do the same botch that you see in the video. This tangled mess has to go. Let's remove the board and replace it with the new construction. I also have to make some mounting holes for it. Hardware-wise, we have done and assembled the upgrade, and now it's time to talk about the code that runs on the coprocessor board that we have added to the 3D printer.
Start the display and also start the two sensors. They have different I2C address, 040 and 041. These are set with the jumpers. This is the beta coefficient that's different for every type of thermistor. You can look that up. And this is the series resistor, or the resistance value at 25 degrees C for your thermistor. And that is the value in ohm for the series resistor. We begin the measurements, begin the display, and in the loop, first thing we are going to do is pull that LED pin low so it turns off. We set function to 0, just a little debounce for the measurements afterwards. And then we read the buttons. And for reading the buttons, I have created this for loop, which checks through all the button pins. And if one of them is low, meaning the button is pressed, it will set the function to that button number. And when we check that button number, we will see that every one of these leads to a new function, like, for example, sing or update power display for the bed. Here we have the functions that are executed. Stop 3D printer is just an M0 command. With serial print line, that's important, and just the command without any other stuff, you can tell a Marlin based 3D printer to execute that command on its usual RX and TX lines. Then we have a load procedure, and we also have an unload procedure. So that's like a custom G code then you can put into this module, but you could also use the M702 or M701 functions that come with Marlin 2.0.
Of course, the 3D printer needs firmware, specifically Marlin 2.0. Here is a rundown on all the settings I did. I'm pretty sure that will get cut down in editing. So here are maybe the highlights, and I put the full version with the complete settings for this machine and some remarks on how to do some of these calibrations or how to determine some settings on the Element 14 community. So if you want to know how to configure Marlin for your machine, give it a watch. Head on over to element14.com/presents, and there you get the full long video.
Here you can define which boot screen you want to show if you have a display connected. In my case, the original display did not work with Marlin 2.0. I don't know why, but I keep it for future projects, and I don't really need it because I put my 3D printer into an Octopi instance, so I can have a much better interface on my computer. The serial port is very important. 0 is the standard port, the one that's used for the USB connection. So if you have your printer tethered, for example, to Octoprint, you need to have serial port 0. If you want to have more than one serial port, you can activate it here by just uncommenting. The baud rate, standard baud rate is 250,000. I have set mine to 115200. Because it's a number that I can easily remember. And also, if you go lower with the baud rate, there is a good chance that your transmission is a little bit more reliable because it's not as error prone. I have only a not very high quality USB cable on there, so I pretty much reckon that it will have some errors. Also, 115200 is the baud rate that in my opinion works best with Octoprint. Really important, prevent cold extrusion. If your extruder or your nozzle is too cold, you will not get filament through there, and you need to be aware of that. If you let your extruder just grind up the filament when it's trying to extrude but it's too cold, that can be a problem, a lot of hassle to clean. So make sure that it's set to a temperature that really lets your filament extrude. If you're printing with PLA, 170 completely okay, 190 would be possibly better. If you're printing with PETG or ABS, maybe set that to 200, 210, should be better. Thermal runner protection. A lot of cheap, not very good 3D printers, you know, the ones that catch on fire, have these things deactivated. And that's the most stupid thing you can do, because this protects you from burning your house down. So thermal protection hot ends basically looks at what is expected. So if I say hot end heat up to that rate, then I know how fast it usually should heat up and how it should react and what I should measure. And if that doesn't matches, then I say, well, there must be an error. Maybe a broken wire, maybe the thermistor is not mounted correctly, maybe something else. I don't know, I don't want to burn the house down. I just switch it off and tell you that there's an error. Now for the end stops. You always need to know which end stops are connected. Usually, that's the most common one. It's the minimum plugs on all three axes, and you need end stop pull-ups, but usually they are connected as normally closed, and when they open, that means they are triggered. On my machine, it's the other way around, because it's an old cheap one. It's normally open, and when it closes, it's triggered. Two main reasons why that is the worst one. It's always better to have them normally closed, because when a wire breaks on your 3D printer on any of these axes, it will say, hey, there's an end stop triggered. So the machine won't run into stuff or will stop.
Hi, I'm David from Element 14 to the Electronics Inside. Join me as I tear down toys, tools, appliances, modern, vintage, classics, and even some new releases, just to find out what's inside.
With every custom printer, or basically every machine that gets built from scratch, first you have to dial in some settings and find the correct values for it to work. So the first print that you're going to do, you can expect that to be pretty much garbage. The first one I did, and I tried out Dave Darko's low poly banana because I think it's a pretty good fast test print. And I tried to make a spoiled banana in glitter PLA, and yeah, it turned out like, yeah, pretty much a piece of garbage. So on the first try, the heat bed started smoking. I knew that this old heat bed had some issues, but now it's completely dead. So the machine started smoking, no panic there. Here's my live reaction. I didn't get the smoke really on camera. What happened is the MOSFET burned out because there is a short in the heat bed. So first troubleshooting is clean your build plate with isopropyl alcohol. You can use just normal alcohol for that, but keep in mind that you need to get rid of all the grease on there, all residue, and don't touch the build plate afterwards. So that's number one. Number two, if you're still having trouble and your build plate is not heated, use a professional adhesive to get that done. And the next step is properly leveling your printer. Here's a time lapse of me doing that with that machine. Basically, you adjust the height of the build plate on all four corners until the little piece of paper that I move around slightly has friction in between there. There is a lot of trial and error involved. A lot of people have their special kind of paper for that task, or even have a professional depth gauge. But I just use whatever paper I have on hand, and if I print at an extrusion rate of 0.3 or 0.35 for the first layer on this machine, I can basically use any copy paper. This machine allows me to give commands via the Octoprint instance, so I can control the printer from my computer, give it print jobs and it just does them. And I can also use the dedicated buttons that we have added to quickly load, unload, home, or do whatever. If something goes wrong, I can just quickly push the G28 or the homing button. Then it injects that G-code into the running G-code. The printer does homing and would then execute the running G-code further. So I can basically make it pause a little bit in between. If I want it to stop, I push G28, and when it's in the home position, at least for 1 or 2 axes, then I press the red button, which is M0, and that is unconditional stop. So for demonstration purposes, I left all the steps per millimeter settings at the default values in Marlin 2.0, and this is what comes out. So you can see the low poly banana model is totally over extruded. It's squished in 2 axes, looks like it. So that's an absolutely disgusting print, but we are going to fix that. The first thing you need to calibrate with every printer, check that if your printer behaves weird or doesn't print as expected, check the steps per millimeter. So I've left the default values in to show you what that does. And I want to emphasize that there are a ton of complicated or more or less complicated procedures out on the web how to calibrate steps, and a lot of them involve printing test cubes and measuring that with a caliper, and then calculating steps and putting them in and measuring a part of filament, extruding that and measuring what's left. All fine and dandy, but there's the main problem behind that. The steps per millimeter are not a value that you measure, it's a value that you calculate, and it's dependent on the mechanical properties of your computer. So all these methods have one fatal flaw: they are not calculated values, they are measuring. And if you measure, you make errors, and those errors translate. So if you make a test cube that's with all these procedures that perfectly 20 by 20 millimeters, plus minus 0.001, if you scale that up and make a cube that is 20 by 20 centimeters, you will have a much bigger error.
These are the standard settings. I showed you that in the video. When you use these settings, you basically get a garbled mess or an over extruded banana with the wrong shape. So the magic is not complicated measuring or whatever a lot of gurus tell you. And there's also, the Germans have like a special G-code that you do, and then you measure things and then you calculate stuff and put it in there at a lot of places. But what actually is, you can calculate all these values depending on your machine. And I'm telling you the standard values, so you don't have to calculate for like most of the Prusa i3 clones. Yeah? It's 100 steps for X, 100 steps for Y, 400 for Z, that's correct. And if you have a direct drive extruder, you need 93. So why I am not setting that to 100 and use 93% flow factor? Because I want to have it correctly for my main filament, which is PLA in that case. So I know I need 93 steps. That's a calculated value that are at a 100% extrusion rate.
So with these values, you can see there are no obscure or fractional values. That's calculated, not measured. So when we put these measures in, reflash the firmware, we can do that with the Arduino IDE, then we get another print. Let's look at how this print goes. Look at that rotten low poly banana, or glittery gray low poly banana. I've also printed a yellow one. This is for reference. The yellow one was printed on the Prusa Mini, which is a 32-bit printer. Just to give you a reference on, that's a very modern printer out of the box. And the gray one, that's my machine after that little step of calibration, meaning leveling, setting the steps per millimeter, and also I used a temperature that I know will work for this filament. I use 210 degrees. In most cases, you will be somewhere between 195 to 215 for PLA, but these varying values are not dependent as much on the filament as you think. Most variance comes from your 3D printer. Not all thermistors are equal, not all connections are equal. That's why I have these special probe connectors, so I can get my reference thermistor in there, can be sure that it has the correct connection and no error is induced there. And then I see what's the difference between the value that my 3D printer tells me and the value that this one measures. And if I know that difference, I can dial that in. And if I know my printer is about 5 degrees off, I just adapt for these 5 degrees and get the same extrusion or the same real temperature as on the other printer where it worked before. So what kind of 3D printer should you get? Easy. You can see that you can basically make any old machine print pretty good to modern standards, but it takes a lot of time and effort. And maybe it's not really worth the hassle or the money. So if you are in the market for a new 3D printer today, I've put some links on the Element 14 community page for some 3D printer models that are pretty good, or I got recommended from others that have them. And if you want to upgrade a machine, always calculate what the parts will cost and a new machine will cost. In that case, that's something to prove a point. It's certainly not worth financially, but it was great to do because it's fun to do and I used up some parts that I have already had around. So always keep in mind that part costs can quickly add up and you might be better off in just getting a new one. But always save the parts because they are great for a lot of other projects. This time we've upgraded a really old broken 3D printer with some basic parts, some custom parts, and did a basic troubleshoot guide on how to get your custom printer to print. And the outcome is surprisingly good. So here's my reference print and here is the print that I got from the machine from today. And they are pretty much on par. Not much difference in there. So if you put in the time and effort, you can make an amazing machine out of your old 3D printer. But consider the cost and maybe it's worth upgrading to a current new machine. Speaking of new machines, I gotta go. There's another project waiting for me.